Find somewhere comfortable. You don't need to follow any of this closely. You don't need to hold on to the details or remember the names or keep track of where we are. Just let the words come to you, the way sound comes through an open window at night. We're going somewhere quiet and vast tonight, somewhere that has no urgency and no demands. If you drift, that's exactly right. If you find yourself half hearing, half dreaming, that's the whole point. Tonight we're going to talk about something hidden inside everything. Inside the air moving slowly in and out of your lungs right now. Inside the blanket over you, the walls around you, the ground beneath the building, the deep rock below that. Inside every star you've ever looked at and every one you haven't. There is a secret written into the structure of matter itself. A mirror image, a twin, a perfect reversal of everything that exists. Physicists call it antimatter, and its story is one of the strangest, most beautiful things our species has ever uncovered. You don't need to sit up for this. You don't need to concentrate. Just let it arrive. Picture a single hydrogen atom. It is the simplest thing in the universe. One proton at the center, a tiny, dense, positively charged particle, and one electron moving around it, negatively charged, so much lighter than the proton that the comparison barely makes sense. The electron is roughly 1,800 times less massive than the proton it orbits. Together they form something electrically neutral, a quiet little system, perfectly balanced. The hydrogen atom is the most common thing in the universe. Most of the stars are made of it. Most of the gas drifting between those stars is made of it. The water in you is partly made of it. It is, in a sense, the universe's default building block, the first word in a very long sentence. Now hold that picture for a moment. One proton, one electron. Small, stable, complete. And now, very quietly, place another atom beside it. One that looks, at first glance, identical. Same size, same mass. The proton at its center weighs exactly the same as the one you were just imagining, and the particle orbiting it is exactly as light as the electron. If you could place them side by side and weigh them, a scale so precise it could measure the breadth of a gnat, they would balance perfectly. They are not the same. The proton at the center of the second atom carries a negative charge, and the particle orbiting it carries a positive one. Everything is reversed, not approximately reversed, not mostly reversed, precisely, completely, perfectly reversed, as though someone had taken the laws of electromagnetism and held them up to a mirror. The second atom is antihydrogen. The particle at its center is an antiproton. The particle in orbit is a positron, sometimes called an anti-electron. And together they form the simplest possible atom of antimatter. What does it mean exactly to say that a particle is the mirror twin of another? It means more than just a reverse charge. Every particle in nature carries a set of properties, numbers in a sense, that describe what kind of thing it is and how it behaves. Charge is the most familiar of these. But there is also something called magnetic moment, which describes how a particle responds to a magnetic field, how it orients itself within one, the way a compass needle orients to the Earth's field. For matter particles, this number points in one direction. For antimatter particles, it points in the other. Then there are deeper properties still, quantities physicists call quantum numbers, which describe things like how a particle interacts with the forces of nature, which families it belongs to, what roles it can play in the dance of subatomic interactions. In every single one of these properties, the antiparticle is the exact opposite of its partner. Not a rough opposite, the precise mathematical negative. The mass, though the mass is the same, this is one of the most quietly remarkable facts in all of physics. Mass is not reversed. The antiproton is just as heavy as the proton. The positron is just as light as the electron. In the mirror of antimatter, mass doesn't flip. Only the charges and the quantum orientations do. It is as though mass is the one thing the universe refuses to invert. Now here is the part that carries a kind of weight, even in the quiet. If those two hydrogen atoms, the ordinary one and the anti-hydrogen one, were ever allowed to touch, they would not simply collide. They would not bounce off each other or combine into something new. They would annihilate, completely, instantly. Every bit of mass in both atoms would convert, in a fraction of a second, into pure energy, bursts of light at the highest energies we know, called gamma rays, shooting outward at the speed of light. Nothing would remain, not a fragment, not a trace, just the light, and then the dark. This is not a metaphor. This is not an approximation. Matter and antimatter, when they meet, erase each other with a totality that nothing else in nature approaches. And yet antimatter is real. It exists. It has been created in laboratories, held in magnetic traps, studied, measured, coaxed into revealing its secrets. The question of where all the antimatter went, why the universe we live in is made almost entirely of ordinary matter when the laws of physics seem to demand equal quantities of both, is one of the deepest unsolved mysteries in all of science. It is a question that touches the reason anything exists at all. The reason there are stars and planets and sleeping bodies in the dark. We'll come to that mystery in time. For now, just hold the image. Two hydrogen atoms side by side, identical in mass, mirror images in everything else, and the knowledge that if they ever touched, they would become light and be gone. There is something in that image that is both deeply strange and, in a quiet way, beautiful. The universe contains its own erasure, built into the fabric of every particle, and somehow, improbably, here we are. In 1928, a young British physicist named Paul Dirac sat down to solve a problem that had been bothering the best minds in physics for several years. The problem was this: quantum theory, the framework that describes how very small things behave, had been developing rapidly through the 1920s. It was strange, counterintuitive, and deeply successful. It explained the behavior of atoms, the way electrons occupy specific energy levels, the way light interacts with matter. But quantum theory, as it stood, had been developed without properly accounting for the effects of special relativity, Einstein's framework for understanding how things behave when they move very fast, close to the speed of light. For most everyday purposes, this didn't matter. Electrons in an atom move slowly enough that relativistic effects are small. But for a complete and rigorous theory, the two frameworks needed to be reconciled. The physics of the very small needed to be made consistent with the physics of the very fast. Dirac was 25 years old. He was known for working alone, for long periods of silence, for an almost monastic focus. His colleagues at Cambridge described him as a man who thought in equations the way others think in sentences. He was not known for warmth, but he was known for a quality that is perhaps more rare, a deep, patient trust in the internal logic of mathematics. If an equation was beautiful, if it was consistent, if it balanced, Dirac believed it was telling the truth about nature, even when what it said seemed impossible. The equation he was trying to write needed to describe an electron in a way that satisfied both quantum theory and special relativity simultaneously. The version of quantum theory that existed at the time, developed by Erwin Schrödinger a few years earlier, worked well for slow-moving particles but broke down at high speeds. Dirac needed something more fundamental. What he found was an equation of striking elegance. It described the electron correctly. It predicted the electron's spin, a quantum property that had been observed experimentally but had never been properly derived from first principles. It predicted the electron's magnetic moment with extraordinary precision. It was, by any measure, a triumph. But it had an uncomfortable feature. When Dirac solved his equation, it produced not one answer, but two. For every electron moving forward in time with positive energy, the mathematics also described a particle with negative energy. Not zero energy, not low energy, negative energy. Negative energy. A particle that would, in principle, lose energy forever, spiraling downward without limit. This was not just strange, it seemed to be physically meaningless. Nothing in the observable world behaved this way. Physicists assumed it was a flaw, an artifact of the mathematics, something that would eventually be explained away. Dirac was not so sure. He sat with the problem for 3 years. The difficulty was profound. If electrons could fall into these negative energy states, why didn't they? An electron in a normal positive energy state should, according to the equations, immediately tumble downward into the negative energy abyss, releasing a burst of light as it went. But electrons didn't do this. They stayed where they were. Something was preventing the collapse. Dirac's solution was audacious. He proposed that all the negative energy states were already full, completely occupied. Every one of them filled with electrons that had been there since the beginning of time. He imagined what he called a sea, an infinite ocean of negative energy electrons, so densely packed that no ordinary electron could fall into it because every available space was already taken. A particle cannot move into a space that is occupied. This is a rule of quantum physics, the Pauli exclusion principle, which says that no two electrons can occupy exactly the same quantum state at the same time. The infinite sea was, in Dirac's picture, the reason the world was stable. This was already a deeply strange idea. But then Dirac asked what would happen if one of those negative energy electrons were knocked out of the sea, if enough energy was supplied to lift it up into the positive energy world we can observe. And that vacancy would behave like a particle in its own right. It would have the mass of an electron, because the absence of an electron mass from the sea creates a gap of that size. But it would carry a positive charge, because the absence of a negative charge is, effectively, a positive one. In 1931, Dirac published a paper suggesting that this hole was real, that it was a particle waiting to be discovered. He called it, tentatively, an anti-electron. He was careful. He hedged. He acknowledged that no such particle had ever been seen. But he followed the equation where it led, even when that direction pointed into territory no one had mapped. The scientific community was not immediately welcoming. Some of Dirac's most distinguished colleagues found the idea implausible. An entire invisible sea of negative energy electrons filling all of space. A mirror image particle that had somehow escaped detection? It seemed like elaborate machinery invented to rescue a flawed theory. There was a particular kind of skepticism reserved for theoretical predictions that seemed to arise purely from mathematical necessity rather than experimental evidence. Physics, the argument went, should be grounded in observation. You couldn't simply conjure a new particle because your equations were misbehaving. But Dirac trusted the mathematics. He had seen it be right before, in ways that surprised everyone, including himself. The equation was too beautiful, too consistent, too precise in its other predictions to be simply wrong about this one thing. He believed the ghost in the numbers was real. He was right. What's worth sitting with, in the quiet, is not just that he was right, but why he was right. He was right because he allowed the internal logic of a set of equations to lead him somewhere that common sense refused to go. He didn't override the mathematics when it said something uncomfortable. He kept following it, patiently, for 3 years, into the dark, and at the end of that path, there was something real. That kind of trust in the slow, careful unfolding of a deep idea is its own kind of courage. On the other side of the Atlantic, in a basement laboratory at the California Institute of Technology in Pasadena, a young experimentalist named Carl Anderson was doing something quite different from Dirac. He wasn't working with equations, he was working with fog. Anderson was 27 years old in 1932, studying the streams of energetic particles that arrive at the Earth's surface from space, what we call cosmic rays. These particles rain down on us constantly, born in the violence of distant supernovae and other astrophysical events, accelerated across the vast distances of the galaxy and arriving at our atmosphere with energies that no laboratory of the era could produce artificially. Anderson wanted to see them, not to detect their presence in the abstract, but to actually see the paths they carved through space. For that, he needed a cloud chamber. A cloud chamber is one of the most elegant instruments in the history of physics. The idea is simple, and the effect is almost magical. You take a sealed container and fill it with air that has been supersaturated with water vapor, meaning the air holds more moisture than it normally could, kept in that delicate, unstable state by careful cooling. The vapor wants to condense into droplets, but it needs something to condense onto, a tiny nucleus, a point of disturbance. Under normal conditions, it just sits there, waiting. Then a charged particle passes through. As it moves, the particle interacts with the atoms of the air, stripping electrons from them, a process called ionization. Each disrupted atom becomes a tiny charged site, and the waiting water vapor seizes on it immediately, condensing into a microscopic droplet. A whole chain of these droplets forms along the particle's path, one after another, like dew forming on a wire in the early morning. The result is a fine, bright thread of mist hanging in the cold air, a track perfectly visible, tracing the exact path the particle took. By placing a powerful magnet around the cloud chamber, Anderson could make the tracks curve. Charged particles moving through a magnetic field are deflected, positive charges curving one way, negative charges curving the other. The degree of curvature also depends on the particle's mass and speed. A heavy particle curves gently, a light one curves sharply. By measuring the arc of a track, Anderson could determine both the charge and, roughly, the mass of whatever had made it. He had been photographing tracks for months. He had seen thousands of them, mostly electrons, occasionally protons, the usual inhabitants of the cosmic ray zoo. He knew what electron tracks looked like. They were delicate, curving easily in the magnetic field, sometimes spiraling as the electrons slowed down. He knew which direction the field bent them. Then, in August of 1932, he saw something that didn't fit. A track curved the wrong way. It had the same delicate quality as an electron track, the same light, graceful arc, the same fine thread of condensed vapor, but it bent in the direction a positive charge would bend, not a negative one. Anderson's first thought was that it might be a proton. But a proton is nearly 2,000 times heavier than an electron, and a proton track looks nothing like this. It curves much more gently. It is coarser, more forceful. This track was light, precise, unmistakably the work of something as slight as an electron. He had placed a lead plate across the middle of the chamber, a slab 6 millimeters thick, to help him determine the direction particles were traveling. A particle passing through lead loses energy, it slows down. The track on one side of the plate would curve more tightly than on the other, and from this he could tell which way it was moving. The anomalous track entered the lead from below, passed through, and emerged above, curving more tightly after the plate, exactly as expected for a particle that had lost energy in the crossing. It was moving upward, and it was positively charged, and it was as light as an electron. There was only one conclusion. It was an electron with a positive charge. Anderson named it the positron. The name was simple, practical, a contraction of positive electron. He published his findings in September 1932 in the journal Physical Review. He had not, at the time of the discovery, read Dirac's 1931 paper. He arrived at the positron not by following a theoretical prediction, but by following a track in the fog. The mathematics and the experiment had found the same thing from opposite directions, like two people walking toward each other through the dark, neither knowing the other was coming. The photograph Anderson published, a single curved white line against a dark background, interrupted by the shadow of the lead plate, is one of the most quietly significant images in the history of science. It doesn't look like much. It looks like a scratch on a chalkboard or a hair caught in the emulsion. But it was the first time a human being had ever seen antimatter, a real antiparticle, real mass, real charge, real trajectory captured in the act of existing. Dirac's ghost had left a footprint. Anderson was awarded the Nobel Prize in Physics in 1936, sharing it with Victor Hess, who had discovered cosmic rays. Dirac had already received his Nobel 3 years earlier in 1933 for the equation that had predicted the positron's existence before anyone had seen it. The two men had never collaborated. They had never needed to. The universe had arranged for them to find the same truth by entirely different paths. What strikes you, sitting quietly with this story, is the image of that track. That single curved line in a cloud of vapor, formed in an instant, photographed, developed, studied. A piece of antimatter, briefly real, briefly visible, and then gone. Annihilated somewhere beyond the frame of the photograph, leaving nothing behind. It existed long enough to be seen. That was enough. Annihilation. The word sounds violent, and in some ways it is, but there is also something in it that is almost serene if you stay with it long enough. Not an explosion in the ordinary sense, not heat, not fire, not the messy chemistry of burning or the slower violence of decay. Something cleaner, something more total. When a particle of matter meets its antiparticle, both of them cease to exist. Not in the way a flame goes out, leaving ash and warm air. They cease to exist in the most complete sense possible. Their mass, all of it, every last fraction, is converted into energy. The conversion is governed by the relationship between mass and energy that Einstein described in 1905, which tells us that mass and energy are not fundamentally different things. They are the same thing in different forms. Mass is, in a sense, frozen energy, and the annihilation of matter and antimatter is the most efficient possible thaw. To get a sense of the scale, consider this. When a single positron meets a single electron, the two particles, each with the same tiny mass, vanish and produce two gamma rays, the most energetic form of electromagnetic radiation, traveling in exactly opposite directions. The gamma rays carry away all the energy that was locked in the mass of both particles. Not most of it, not almost all of it, all of it. The conversion is 100%. No other process in nature achieves this. Nuclear fission, the splitting of heavy atoms, converts less than 1% of mass into energy. Nuclear fusion, the process that powers stars, converts somewhat less than 1% as well. Annihilation converts everything. The gamma rays produced always travel in precisely opposite directions. This is not an accident. It is a consequence of a principle called conservation of momentum, the idea that the total momentum of a system before an event must equal the total momentum after. If a positron and an electron are moving toward each other with roughly equal and opposite velocities, their combined momentum is close to zero. After annihilation, the two gamma rays must carry zero total momentum between them, which means they must travel in opposite directions with equal energies. The gamma rays are always paired, always opposite, always equal. This precision, this perfect symmetry of the outgoing light, turns out to be extraordinarily useful. In hospitals around the world, a technology called positron emission tomography, PET scanning, uses exactly this process to build three-dimensional images of living tissue. A patient is given a small amount of a radioactive substance, usually a form of glucose modified to carry a radioactive atom that decays by emitting positrons. The substance travels through the bloodstream and accumulates in tissues that are metabolically active, tissues burning energy like tumors or active regions of the brain. As the radioactive atoms decay, they emit positrons that travel only a tiny distance, a fraction of a millimeter, before meeting electrons in the surrounding tissue. Two gamma rays shoot out in opposite directions. Around the patient, a ring of detectors waits. When two detectors on opposite sides of the ring register a gamma ray at almost exactly the same moment, the scanner knows that an annihilation occurred somewhere along the line connecting those two detectors. By recording thousands of these paired detections and triangulating, the computer builds up a map of where the radioactive substance has concentrated. The result is a three-dimensional image of metabolic activity, not anatomy, not structure, but function. Living chemistry made visible by antimatter. It is a remarkable thing to hold in mind, the same process that would, in principle, erase the universe if matter and antimatter ever met in equal quantities. That total, efficient, complete annihilation is being used right now in hospitals to illuminate the interior of the human body. Antimatter is saving lives. Now consider the scale of the energy involved if the annihilation were not microscopic but macroscopic. A single gram of matter annihilating completely with a single gram of antimatter would release an amount of energy comparable to a large nuclear weapon. The mathematics of Einstein's mass-energy relationship makes this plain. Even a tiny mass multiplied by the square of the speed of light, which is a very large number indeed, yields an enormous energy. 2 grams of mass, completely converted, releases energy on a scale that is genuinely difficult to hold in the mind. And yet, all the antimatter ever produced by human beings, in all the particle accelerators ever built, across all the decades of effort, amounts to something in the range of a few billionths of a gram, a quantity so small it would not be visible to the naked eye. If all of it were annihilated at once, the energy released would be enough to warm a cup of tea, perhaps not even that. The gap between the energy potential of antimatter and our ability to produce it is so vast that it makes the concept of antimatter as a weapon or a fuel source something that belongs firmly in the distant imaginative future, not in any present reality. There is also a gentler kind of annihilation worth knowing about. Positronium, a fleeting, ghostly atom made of one electron and one positron orbiting each other, exists briefly before the two particles annihilate. It lasts, on average, less than a millionth of a second. In that vanishingly short time, it is, technically, a real atom. It has energy levels. It absorbs and emits light at specific frequencies. It obeys the same quantum rules as hydrogen, and then it is gone, leaving 2 gamma rays and nothing else. There is something in that image that lingers, 2 opposites, briefly together, briefly real, then light. Here is the question that keeps physicists awake in a different sense than the one that brings most of us to this channel. In the first moments after the Big Bang, in the first fractions of a second, when the universe was unimaginably hot and dense, a fireball of pure energy, particles and antiparticles were being created continuously. Gamma rays of sufficient energy spontaneously produced pairs, an electron and a positron, a proton and an antiproton, quarks and antiproton, quarks and antiproton. The process was constant, frantic, and governed by the same physics we can study today. And that physics is, to a very good approximation, symmetric. For every particle produced, an antiparticle was produced. The universe, in those first moments, should have contained matter and antimatter in precisely equal quantities. If that symmetry had held perfectly, you can work out what would have happened next. As the universe expanded and cooled, the matter and antimatter would have found each other and annihilated. All of it. Every proton would have met an antiproton. Every electron would have met a positron. The annihilation would have been total, leaving the universe filled with gamma radiation and nothing else. No atoms, no molecules, no stars, no planets, no oceans, no sleeping bodies, no one to wonder about any of it. And yet here we are. The universe is not empty. It is full of matter. Galaxies and gas clouds and planets and you. Observations suggest that there are essentially no large structures made of antimatter anywhere in the observable universe. The nearest known antimatter to us is produced in tiny quantities in cosmic ray collisions or in particle accelerators. The universe overwhelmingly chose matter. This means the symmetry was broken. Somewhere in the first second of the universe's existence, something happened that meant matter was produced in slightly greater quantities than antimatter, not enormously greater. The imbalance, as best as physicists can estimate, was something like 1 extra matter particle for every billion matter, antimatter pairs, 1 in a billion. The billion pairs annihilated each other, filling the universe with the cosmic microwave background radiation we can still detect today, the faint afterglow of all that annihilation, and the one remaining matter particle, that tiny surplus, that rounding error in the arithmetic of creation, became everything. The stars, the periodic table, you. The question is why? What broke the symmetry? What tilted the scales, even that tiny amount, in favor of matter? Physicists have identified a necessary condition for this to have happened, a set of requirements that any explanation must satisfy. One of those requirements is something called CP violation, and it is worth taking a moment with this idea because it is subtle and important. CP stands for charge parity. Charge symmetry means that if you replace every particle with its antiparticle, the laws of physics should look the same. Parity symmetry means that if you reverse the spatial coordinates of a system, replace left with right, up with down, the physics should again be unchanged. CP symmetry combines both, replace particles with antiparticles and mirror. Reverse the coordinates simultaneously and everything should look the same. For most interactions, this is true, but in the 1960s, experiments studying particles called kaons, a type of particle made of quarks and antiquarks bound together, found that CP symmetry was violated in certain rare decays. The particles did not behave the same as their antiparticle equivalents. The asymmetry was tiny but real, and it was confirmed. The universe's laws are not perfectly symmetric between matter and antimatter. There is a genuine, measurable difference. Since then, experiments studying particles called B mesons, heavier cousins of kaons, also made of bound quark-antiquark pairs produced at dedicated particle colliders, have confirmed and measured CP violation in greater detail. The Baybar experiment in California and the Bell experiment in Japan spent years studying billions of B meson decays, looking for the subtle differences in how matter and antimatter behave. They found them. The asymmetries are real. Matter and antimatter are not perfectly equal under the laws of physics. The difficulty is that the CP violation we have measured so far is not large enough. The asymmetry seen in kaons and B mesons is real, but it is far too small, by many orders of magnitude, to account for the matter-antimatter imbalance of the universe. Something is still missing. There must be additional sources of CP violation that we have not yet found, operating in parts of physics we have not yet fully explored. This is where the story rests, honestly and openly. We know the symmetry was broken. We know it must have been, because we exist. We have found evidence of asymmetry in certain particle decays, but we cannot yet explain the full magnitude of what happened in that first second. The answer is somewhere in the physics we don't yet understand, in experiments not yet built, in equations not yet written. The universe chose matter over antimatter for reasons we are still learning to read, and that openness, that genuine not knowing, is not a failure. It is an invitation. The question is still alive. Under the hills near Geneva, in a ring of tunnels and detector halls that stretches for kilometers beneath the Swiss and French countryside, there is a place called the Antimatter Factory. It belongs to CERN, the European Organization for Nuclear Research, and it is one of the most extraordinary scientific facilities ever built. Its purpose is to create antimatter, slow it down, and study it before it has a chance to annihilate. Making antimatter requires energy, a great deal of it. The process begins with ordinary protons, the same kind that sit in the nuclei of every hydrogen atom. These protons are accelerated to very close to the speed of light inside a machine called the proton synchrotron, a circular accelerator that uses powerful magnetic fields to bend the protons around a ring and electric fields to kick them faster on each pass. When they have reached the required energy, they are fired at a fixed metal target, typically iridium, an extremely dense metal. The collision is violent. The protons strike the nuclei of the iridium atoms with enough energy that the impact produces a spray of new particles, a debris field of protons, neutrons, pions, kaons, and, occasionally, antiprotons. They are rare. For every million or so protons fired at the target, perhaps a few dozen antiprotons emerge in a useful direction. These antiprotons are then separated from the debris using magnetic fields. Antiprotons curve the opposite way to protons in a magnetic field, which makes them identifiable and collected into a storage ring, but they are moving far too fast to be useful. A fast antiproton is almost impossible to trap. It would hit the walls of any container almost immediately and annihilate. To study antimatter, you need it cold, slow. The process of slowing the antiprotons down is called cooling, and it is one of the more ingenious techniques in modern physics. One method, called stochastic cooling, stochastic simply meaning that it uses statistical methods, works by detecting the average motion of the antiproton cloud and sending a corrective signal across the ring to nudge the particles toward the center of their distribution, gently herding them toward a common speed. Another method uses electrons. The antiprotons are passed through a dense beam of electrons moving at the same average velocity, and through repeated small interactions, the antiprotons gradually lose energy to the electron beam, the way a fast-moving ball bearing loses speed passing through a tub of sand. After many cycles of slowing and cooling, the antiprotons are cold enough, moving slowly enough to be held in a magnetic trap. The trap uses carefully shaped magnetic fields to create a region of space where the antiprotons can circulate without touching any material surface. It is a cage made entirely of force, with no walls. The antiprotons orbit inside it, isolated from ordinary matter for minutes or hours at a time. To make antihydrogen, the simplest antimatter atom, you need to add a positron. Positrons are easier to produce. They emerge naturally from the decay of certain radioactive isotopes, and they can be accumulated in their own magnetic trap. Once you have a cloud of cold antiprotons and a cloud of cold positrons, you can bring them together inside a device called a penning trap, a combination of electric and magnetic fields that can hold charged particles of both signs simultaneously. Under the right conditions, an antiproton will capture a positron into orbit around it, forming an antihydrogen atom. This first happens in 1995 at CERN, when 9 antihydrogen atoms were produced and detected. It was a landmark. But 9 atoms, existing for nanoseconds before annihilating on the walls of the apparatus, were not enough to study in any meaningful way. What physicists needed was to trap the antiatoms. An antihydrogen atom is electrically neutral. It carries no net charge, so it cannot be held by electric fields alone. But it does have a very slight magnetic moment, the same tiny compass needle property we discussed at the beginning. Neutral atoms with magnetic moments can be trapped in a region where the magnetic field has a local minimum, They are drawn toward the weakest point in the field and held there the way a marble settles into a bowl. The magnetic force is extremely weak for neutral atoms, which means the trap only works if the atoms are moving very slowly, which means they need to be very cold, at temperatures within a fraction of a degree of absolute zero, the coldest temperature possible. The Alpha collaboration at CERN achieved this in 2010, trapping anti-hydrogen atoms for the first time. By 2011, they were holding them for over 15 minutes. The effort required to reach that point, years of designing and building ever more precise traps, cooling systems, and detection methods, all overstate. Every component had to function with extraordinary reliability, because a single vibration, a single stray magnetic field, a single molecule of ordinary gas drifting into the trap could end the experiment instantly in a flash of annihilation. And what you can do with those trapped anti-atoms, those few dozen or few hundred anti-hydrogen atoms, floating in their magnetic bowl in a near-perfect vacuum at a temperature close to absolute zero, is measure them. Shine a carefully tuned laser on them. Watch how they absorb and re-emit light. Compare their spectral properties to ordinary hydrogen, measured to extraordinary precision over many decades. Ask whether the inner light of antimatter is truly identical to the inner light of matter, or whether some tiny difference might be hiding there, whispering the answer to the deepest question in cosmology. The patience required for this work is its own kind of wonder. Years of effort, millions of euros of equipment, hundreds of scientists, to hold a handful of atoms for a few minutes and listen to what they have to say. For a long time, one of the most basic questions you could ask about antimatter had no answer. Does it fall? It seems like it should have an obvious answer. Gravity pulls things down, everything falls. Apples, planets, light itself is bent by gravity. Why would antimatter be any different? But the honest answer for most of the history of antimatter physics was that no one had actually checked. The question was genuinely open, and some serious theoretical ideas suggested it might not be as obvious as it sounds. There are speculative frameworks, not mainstream physics, but not entirely without motivation either, in which antimatter might be gravitationally repelled by ordinary matter rather than attracted to it. If antimatter experienced a kind of anti-gravity, falling upward instead of downward, it might explain why we don't see large quantities of it in the universe. Perhaps antimatter was pushed away from matter in the early universe by gravitational repulsion, and the two never had the chance to annihilate completely. This idea was never widely accepted. Einstein's general theory of relativity, our most complete description of gravity, predicts that gravity should affect all forms of mass energy identically, regardless of whether that energy is in the form of matter or antimatter. The theory makes no distinction. But general relativity had never been directly tested with antimatter, and in physics, an untested prediction is still a prediction, not a fact. The question deserved an experiment. The difficulty was that testing gravity with antimatter required doing something that had taken decades to achieve in the first place, making cold, neutral antiatoms and holding them long enough to watch what they did when you let them go. By 2023, the Alpha collaboration had been refining their anti-hydrogen traps for over a decade. They had a new apparatus called Alpha GA, the G for gravitational acceleration, the quantity they wanted to measure. The design was elegant in its simplicity. They built a tall vertical tube about 25 centimeters from top to bottom, surrounded by the magnetic trap. Anti-hydrogen atoms were produced, cooled, and captured in the usual way. Then, very carefully, the magnetic trap was adjusted, not switched off abruptly, which would send the atoms flying, but ramped down slowly, gently reducing the strength of the confining fields over several seconds. As the trap weakened, the antiatoms began to drift. those that drifted toward the top of the tube or toward the bottom would eventually reach a point where the residual magnetic fields were too weak to hold them, and they would touch the tube wall and annihilate, producing a flash of gamma rays that the detectors surrounding the tube could register. The question was simply, do more antiatoms annihilate at the bottom of the tube than the top? If antimatter fell downward under gravity, the answer would be yes. Gravity would pull the antiatoms toward the floor of the tube, and they would annihilate at the bottom more often than the top. If antimatter fell upward, experienced antigravity. If gravity had no effect on antimatter at all, the annihilations would be distributed symmetrically. The result, published in September 2023 in the journal Nature, was clear. The antiatoms fell downward. More annihilations were observed at the bottom of the tube than the top, in a pattern consistent with ordinary gravitational acceleration. The measurement had a precision of about 25%, meaning the result was consistent with antihydrogen falling at the same rate as ordinary hydrogen, give or take a quarter of that rate. Not a precision measurement, but a definitive directional answer. Antimatter falls down. The result was at once expected and deeply satisfying. Expected because general relativity predicted it. Satisfying because no one had ever actually seen it happen before. The Alpha team had watched antimatter fall. They had measured its response to gravity with their own instruments, with their own antiatoms, in a tube in a laboratory in Geneva. The universe had been asked a direct question and had answered directly. The anti-gravity hypothesis for explaining the matter, antimatter asymmetry, was not ruled out entirely by this single measurement. The precision was not yet high enough for that, but it was significantly constrained. And the collaboration immediately began planning the next stage of measurements, working toward a precision of a few percent or better, at which point the comparison with ordinary matter would become truly rigorous. Alongside the gravitational work, the Alpha collaboration has continued their spectroscopic studies of antihydrogen, shining lasers of precisely known frequencies at their trapped antiatoms and measuring which frequencies the atoms absorb. In ordinary hydrogen, the energy difference between the lowest and second lowest energy levels of the electron, the gap that produces the famous ultraviolet light called the Lyman alpha line, has been measured with extraordinary precision over many decades. If antihydrogen absorbs light at a slightly different frequency, even by the tiniest amount, it would be a sign that matter and antimatter are not perfectly symmetric in their internal structure. It would be a hint toward new physics. In May 2026, the Alpha collaboration announced a 100-fold improvement in the precision of their measurement of this energy gap in antihydrogen, a result that brought the comparison between hydrogen and antihydrogen to a level of detail never before achieved. And the answer to that 100-fold greater precision was the same. Antihydrogen and hydrogen absorb light at frequencies that are indistinguishable within the measurement's uncertainty. Which means the asymmetry, if it exists in the structure of the atom, is smaller still than anyone has yet been able to see. The search continues. The instruments grow more sensitive. The antiatoms are held a little longer each year, studied a little more carefully, asked a little more precisely to reveal whatever secret they are keeping. And each measurement, each careful comparison of matter and antimatter is a small act of listening, patient, unhurried, conducted in the deep cold of a laboratory where a handful of the rarest atoms ever made drift quietly in a magnetic field, waiting to be understood. Come back, for a moment, to the image from the beginning. Two hydrogen atoms, side by side. One ordinary, a proton and an electron, the simplest structure matter knows how to make. One inverted, an antiproton and a positron, identical in every measurable weight, opposite in every measurable quality. Two atoms so nearly alike that only the most sensitive instruments could tell them apart at a distance. Two atoms that, if brought together, would erase each other completely in a flash of gamma light, leaving the universe exactly as though neither had ever existed. Hold that image and then let it expand. Let it grow outward from those two atoms to the scale of the early universe, a space dense with light and heat and particle pairs, matter and antimatter born together in equal measure, a billion times a billion times a billion pairs in every direction, annihilating and being born and annihilating again in the first fractions of a second after everything began. And somewhere in that vast, symmetric fire, something tilted, something in the laws of physics, something we have not yet fully understood, produced one extra matter particle for every billion pairs. The billion pairs annihilated, the one remained. And that remainder became everything. The hydrogen clouds that drifted in the darkness for hundreds of millions of years, the first stars that ignited when those clouds grew dense enough to fuse, the heavier elements forged in those stars and scattered when the stars died, the planets that formed from that scattered material, the oceans and the chemistry and the long, slow emergence of life, the sleeping body in the dark. You are the remainder. There is something in that fact that is very hard to hold and very hard to let go of. You exist because of an asymmetry so small that it took the universe a billion particle pairs to produce a single survivor. You are made of matter that won a lottery whose rules we are still learning to read in a competition that was decided in the first second of time. Antimatter is not distant from this. It is not a laboratory curiosity or a theoretical abstraction. It is woven into the fabric of the ordinary world, closer than you might think. It rains down on you from space, cosmic rays, energetic particles arriving from supernovae and other violent events across the galaxy, include positrons among their number. They arrive at the top of the atmosphere constantly, producing showers of secondary particles as they collide with the air. Some of those positrons reach the surface. Antimatter falls on you, gently, continuously from the sky. Above thunderstorms, something even stranger happens. The intense electric fields generated by large storms can accelerate electrons to high enough energies that, when they collide with atomic nuclei in the air, they produce gamma rays energetic enough to spontaneously create electron-positron pairs. The same storms that send lightning down to the ground are quietly producing positrons in the clouds above, in quantities small enough to be harmless, but real enough to be detected by instruments on satellites. Antimatter is also made in your kitchen, or rather in the potassium that sits in a banana on the counter, or in the potassium distributed through your own body. Potassium exists in nature as a mixture of isotopes, and one of those isotopes, it decays by a process that occasionally emits a positron. A banana, with its modest potassium content, emits a positron roughly once every 75 minutes. Your body, with considerably more potassium in it, does the same, in a quiet, continuous, imperceptible way. You are, at this moment, a very faint source of antimatter. The positrons annihilate almost immediately against electrons in the surrounding tissue, producing paired gamma rays that pass through you without harm. But the antimatter is there. It has always been there. It is part of the ordinary chemistry of living things. And somewhere, perhaps, there is an anti-star, a star made entirely of antimatter, anti-hydrogen fusing into anti-helium in its core, light pouring from its surface, indistinguishable from the light of any ordinary star. If it existed, it would shine. It would warm any planet near it. It would warm any planet near it. It would look, from a distance, exactly like the sun. Light, after all, is its own antiparticle. A photon is identical to its antimatter counterpart. The only way to know an anti-star from a star would be to find the border where its light met ordinary matter and watch the annihilation glow of the boundary. Physicists have searched for signs of this in the cosmic ray data, looking for anti-helium nuclei that would be too heavy to have been produced by cosmic ray collisions and could only have come from an antimatter star. So far, nothing definitive. But the search continues. The instruments grow more sensitive. The night is very quiet now. Think of all the layers of this, the particle and its twin, the equation that predicted a ghost, the fog chamber and the curved white line, the annihilation that powers the scanners in hospitals, the asymmetry in the early universe that left a remainder of 1 in a billion, the patient scientists in Geneva cooling antiprotons to temperatures near absolute zero, building magnetic cages out of pure force, watching antiatoms drift slowly downward under gravity. The 100-fold improvement in a measurement of light absorbed by antimatter, confirming once again that the inner life of the anti-universe looks, so far, like a mirror of our own. And underneath all of it, still unanswered, still open, still alive, why did matter win? We don't know, not fully. We know that the laws of physics are not perfectly symmetric between matter and antimatter. We have measured that asymmetry in particle decays. We know the imbalance was tiny, 1 in a billion. We know it was enough. But the exact mechanism, the specific process in the first second of the universe that tipped the scales, remains beyond our reach. It is one of the few places in physics where the honest answer is still simply, we don't know yet. There is a strange comfort in that, not in the not knowing itself, but in the fact that the question is still open, still being worked on, still drawing careful people into cold laboratories to hold antimatter in magnetic cages and listen to its light. The asymmetry that made you possible is still being investigated, one careful measurement at a time. You are here, in a bed, in a room, in a building, on a planet that formed from the scattered remains of dead stars, in a galaxy among hundreds of billions of galaxies, in a universe that almost wasn't, made of particles that survived a lottery held in the first second of time. The questions don't need answering tonight. The atoms in you, the hydrogen and carbon and oxygen and potassium, have been here for billions of years in various forms, and they will be here for billions more. The particular arrangement that is you, reading or listening or drifting in the dark, is temporary and extraordinary and made of stuff that won against its own mirror image before the first star was born. The universe is very old. The questions are very deep. The night is very patient. And so we leave it there. Somewhere behind you, the day has already grown distant and soft. The asymmetry that made you possible is doing its quiet work, as it always has. Sleep well.